driving semiconductor growth. We'll talk about VLSI design flow. During the VLSI design flow, I will start from a general flow which has a lot of steps which are particular to ASIC design flow, but then I will go into specific aspect like how does this flow differ in for analog components, how does this flow when you're doing differ slightly when you're doing FPGA, but our major focus will be towards ASIC design flow, but I'll keep pointing out and talk about specific like analog devices you're working on, soft IPs you're working on, hard IPs you're working on. I'll try to differentiate and talk about how the steps would be different as well. So let's start with overview of the design flow. So typically, when you're designing a chip or a product, let's say you're designing a iPhone, right? So you will start with something known as specification. What is my device needs to do? For example, for cell phone, you would say, okay, it needs to make calls. It should be able to browse to the internet. It should be able to access data. You should be able to create applications on it. What will be the size of it? What will be the weight of it? How long can it survive in terms of battery life? All those things go into what is known as your specification. Okay, so you start with specification. Then based upon specification, your people who are working on the architecture level, they will decide what should be the architecture of the device, like how much memory you will need, what kind of battery you will need, what kind of other components you will need, what kind of ports you will need, whether it will connect to USB or not. That all goes into architecture, and that is basically done at a high level by your chip architects. Sometimes it's a team, sometimes it's maybe a couple of people or one person, depending upon which company it is, how big the company is. But you start with specification, which is driven by market requirement in terms of what is market looking for. Is the market looking for a bigger screen? Is the people looking for a smaller screen? All that basically marketing people and the people who are in the field figure out, and based upon that decide the specification, and then that specification goes into architecture. Then once that architecture is done, basically you start designing your chip and you start writing code for your chip, which is in an ASIC flow typically done by writing RTL for your design, reusing RTL for your design. Then you do linting of RTL. I will talk about what is linting, what is RTL. I'll go into details of each step as we go along. But at a high level, basically you start writing RTL for your design, and I'll talk about what is RTL. Then once that is done, you actually, whatever you have coded, you have to verify to make sure as in whatever the specifications were matches with what you have written here. So that is the verification step. There are multiple types of verification, as in simulation, static verification, emulation, formal verification. We'll go into those details of those topics. Then after verification, you right now have basically a code, just a code, right? As in if you think coming from the software background, it's like C++ code. Here it's your Verilog or VHDL code. Now this code needs to go into hardware or real silicon. So the code is at a very high abstraction level that needs to be converted into a layer which can be finally be put on silicon. So in order to do that, there are multiple steps which are done. First step for that is synthesis. So far, till verification, till here, these steps are not dependent upon the technology you are building your device for. For example, the same steps can be for 45 nanometer and 90 nanometer. Steps are not, basically the code may stay the same. But after you're done with verification, you go into a step known as logic synthesis, which maps your code or RTL you have written to actual gates in the design, AND gate, NAND gate, flip-flop. And starting from this step, you start getting closer to the technology you will be working on. So synthesis, once you do synthesis, you will actually be mapping your RTL to specific technology library on which your device will be finally fabricated or manufactured. During this, you also basically do DFT. We'll talk about DFT, which is important for improving quality of your devices, reliability of your devices. Then you do equivalence checking, which is kind of verification for synthesis. You add low power related stuff if needed. So all these steps we'll talk about. So basically after verification, you go into synthesis. Then you do something called timing analysis, and we'll talk about what are the details of that. What do you check in that? How do you check do timing analysis? Basically, you're ensuring your chip is running at a frequency you wanted it to run it. For example, you were designing a processor, and processor needs to run at 1 gigahertz. You need to make sure, and timing analysis at that point ensures that processor runs at 1 gigahertz. Then you will get more close to the real silicon, how it will look on the real silicon. You do something, a step known as place and route, where basically you put place, how the wires will be connected, how the power will be connected, how clock will propagate further in the design, and that it's basically the physical design of your chip, physically how it will look like, where each thing would be. And if you open up a chip, this is how it is going to look like in terms of where each of the components are, and this is done during place and route. So that's why it's also known as physical design, because now you're physically placing your blocks, connecting those things, which is how it will look like in real silicon. Then after that, you do timing analysis again to ensure, as in basically you're meeting timing with the physical placement. Information coming from the place and route tool will be used. Then you do other sign-off checks, like you're ensuring you are meeting design rule checks, which are specified by foundry. Your design is good to be manufactured. All those checks you will do to make sure, since it's a complex process, there can be mistakes anywhere. You need, everything has to be verified by different means before it goes into the foundry. Then you do gate level verification also. This is after basically similar to art verification you were doing here at RTL, but now you are doing at the netlist level, or at the level which will go into silicon. And we'll talk about, and we'll go into details of that as well. Then you go put the device, give it the device for fabrication. This is as in if you have, like if your company usually has your own foundry, the fabrication will go there, like for Intel or for Samsung. But if you are just a company which does not have a foundry, typically you will go to TSMC is the biggest foundry. Typically you will go there. But there are others, like you might go to Samsung. So there are 3 or 4 major foundries there, which actually fabricate the chips. With the major one is TSMC, then there is Samsung, there is Global Foundry, and basically chip will go for fabrication here. There are some smaller foundries here and there, but these are the major foundries where the chips are fabricated. By we'll talk about what is the fabrication step, what are the things which are done during fabrication. Once the fabrication is done, you package the chip. Package where you put a casing around the chip so the outside environment does not destroy it or does not change the behavior of the chip. And then you test the chip to make sure when you're shipping it to the customer, it's working correctly, it's working at the performance frequency you wanted, and doing the job which you wanted it to do. So this is a very high level overview of VLSI design flow. Let's say if you're working at IP level, you might be doing this flow slightly differently. I'll talk about if you're making hard IP, this might be slightly different. If you're working at an analog, it might be slightly different. I'll go into those nuances. But this is the high level overview of what is done in the VLSI flow. And we'll go into details of each of these steps a little bit later. Let me just take a minute of break just to make sure no one is waiting to join the meeting. And actually there are, so just a minute. Just want to give me a second break so that I can actually admit all these people. Oops. Just a minute. Okay, I'm just trying. Okay, so I admitted whomever I could. Okay, let me come back to the presentation. So there is a question, what is linting? We'll go into that, as in I'll talk about what is linting and what are each of these steps. Then sometimes there is a step known as ECO, where basically you are doing a lot of verification. If based upon that verification you need to fix something in the design, that is known as engineering change order. And we'll talk about that step as well. So let's talk about what are the various kind of flows, things which are there in VLSI chip designing. Then basically we'll go into more detail. There is a question, what is basically digital chip design flow? The flow I just talked about is actually mostly digital chip design flow. Analog chip, hard IP is slightly different. So let's talk about what are the various kind of basically companies or the IPs which exist in the design flow. So one IP is known as soft IP. Okay, soft IP, or also there is similar term used as firm IP. These are the two kind of IPs where basically there are a lot of companies who don't basically give you, as in let's say ARM, right? ARM does not give you a silicon or a chip. They sell something which is known as soft IP. Okay, soft IP is basically an IP which is given in a form where user can just take that IP either in the form of RTL or in the form of the netlist, okay, and use that for their design. For example, Apple takes for some of its devices the IP from ARM. What ARM provides is not a chip, not a physical chip, but they provide their RTL, the surrounding things which are needed with RTL. And usually in soft IP, RTL or netlist is the main information which is provided. But in addition to that, what else is provided is the documents related to your IP, how the IP works, maybe architecture documents, those kind of information are also provided with your IP. Okay, so that is a soft IP where basically usually RTL or netlist is provided. If netlist is provided, it is usually known as firm IP because you kind of linked it to the technology. But if you are providing RTL, it's not linked to the technology. The advantage of that is, let's say you're working with 45 nanometer, you can use the same IP. You are working on 4 nanometer, you can use the same IP. Some of these examples like ARM I talked about, then Synopsys also provide designware components, and these usually are highly parameterizable. I mean, since you're providing to multiple companies, the RTL is written in such a way that it can be configured automatically based upon parameters for your use. For example, some may use for ARM, if let's say they're providing, some may use different kind of ports, some may use faster processing and additional components. All these can be configured in your design by using certain parameter. So it's highly reusable across technology, it's highly customizable. And there are a lot of companies which purely just do soft IP. Basically, they create an IP and they sell it to their customer as an IP, providing a physical chip to their customer. So what is a soft IP flow? So we talked about the general flow, and that was a general digital IPs flow. But some of the flows, let's say if you're doing now soft IP, is going to be slightly different. It's not going to be very different, but slightly different. So for example, you will write specification, you will do architecture, you will do RTL design and linting. We'll go into details of each of these steps, but I'm trying to make sure you appreciate the idea that each of the flows can be slightly different. But overall, if you know the flow, you can work for any of these companies and understand what they're doing. Since it's a soft IP company, you will finally either provide RTL or netlist and other related information. So if you're providing netlist, you will do logic synthesis and timing analysis and then provide netlist. If you're just providing RTL, you will stop at this step and just provide RTL and other related information for the block. So the flow becomes slightly lesser. Because you're not giving a physical chip, but you're giving an IP. And so the step at which you stop comes slightly earlier in the flow. So once you provide this information, the company, let's say Apple, is taking that IP, putting it in their chip, and then they will do rest of the step. They will do static timing analysis, then they will do fabrication. All that is then done by the customer who is taking that IP. But you will stop at an earlier step. Let's say if you're giving soft IP, you will stop at RTL. If you're giving firm IP, you will give netlist, which is mapped to the gate level. Similar to soft IPs, there is something known as hard IPs. Okay, so hard IPs are slightly more it's the next step after soft IP, where basically hard IPs are hardened by a process known as IP hardening. And hardening is nothing but basically you map it to a technology. Okay, so let's say I wrote some RTL, and then IP I'm providing is going to work only, let's say, on 45 nanometer technology, because I've designed the IP using the gates of that technology. That is known as the hardening process. So unlike soft IP, you have mapped it to the gate level, and that in a gate level, and basically you have also physically designed it. You actually connected the physical placement of various things, and that is what you are selling. That is known as hard IP. So if you're selling RTL over netlist, and that is your end product, that is known as soft or firm IP, but you physically design it so that customer can just plug it into their environment, and it's physical, and it's done after physical designing, that is known as hard IP. So in hard IP, you will provide kind of layout format, which is typically GDS information you will give, Liberty information you will give, LEF format you will give. These are nothing but after place and route or after physical design, this information is generated, and that is the information you're selling to the customer. So it's highly dependent upon technology, because physical design is dependent upon technology. So once you're giving an IP, you will have, it's not configurable that you can use it on any technology. If you are given it for 45 nanometer, it will only work on 45 nanometer. So it's not parameterizable. If your customer wants a different kind of components, you will have to redesign and then give a separate hard IP. Same hard IP cannot work across technology, across a different kind of blocks. So it's kind of very fixed. So that's why it's not known as hard, because you cannot change it too much. And versus soft, where you can modify your RTL to change the IP. So usually analog IPs and mixed signal IPs are hard IPs, because it needs a lot of dedication to make it work in a particular technology. Like USB, PCI usually are sold in form of hard IPs. And the thing is, if let's say technology changes, you will have to design a new hard IP and then sell it. Now, since it's hard IP, it's linked to a technology, the steps I said is a subset of overall VLSI design flow. So steps would be, now you will stop after place and route. So you will do specification, architecture, design of that, you will verify it, you will do logical synthesis, which is corresponding to your technology, timing analysis, you will place and route, you will do all the sign-off checks which are needed, gate level verification, and then that is what you will ship. So basically, you're not doing fabrication yourself, but you've done most of the steps in terms of place and route, verification at the place after place and route, and you will give layout information or this kind of information which is generated after place and route to your customer, so that they can integrate in their chip. Your customer to whom you are giving will integrate this and then take it to fabrication or foundry. So that is the hard IP flow. But as you can appreciate, right, overall steps are the same. Slightly they'll differ depending upon what is your end product, what is the IP, or what is it you are selling. Then analog IPs. So far we have talked about the flows which are more suited for digital IPs. Analog IPs, of course, since these are analog, they're designed slightly differently. Analog, the tool chains which or the tools you use are also slightly different, and the specification are also slightly different. You talk about as in when you're designing an analog IP, for example, a PHY physical layer for you, let's say USB. You will talk about what is my noise margin, what is the gain, what is the current it can draw. So and the tool chains used to design those things are also different. So typically you will directly create schematic, you will use mathematical equations and functions to design that circuit. It's more closer to what we have started learning during college, if you remember analog designs, op-amps and those kind of things. So analog designs deal with continuous time signals, and the circuits are designed to basically either generate, either you measure, or either you amplify or change those signals which occur in the real life naturally, which are analog signals. While digital circuits deal with discrete time signals, like 0 and 1 is all they care about. And you design circuits to do mathematical analysis using Boolean algebra. But here it's the real time analysis in analog circuit. Like some examples of, and as a major advantage example of analog circuit is your data converters, which converts analog to digital or digital to analog. And these are sold as analog chips or analog blocks. Okay. Typically, these are hard IPs, or you sell the full chip directly. Texas Instruments is one of the major player, which is, basically works in which has a lot of analog IPs and mixed signal devices. So what is the flow? How the flow is different for analog device now, right? So you start with specification, but rather than writing RTL, you will do something known as schematic design. There are multiple tools like Caliber and schematic tools from Mentor, which is very popular. You do schematic design where basically you will add your transistors, simulate the behavior, and then basically go into physical implementation, generate a GDS. If you are basically selling it as a hard IP, you will sell this to your customer. But if you're selling a full chip, as in the full component, which goes in, then you take it to the foundry, fabricate it, and then give it to your customer. So analog IP, then flow is slightly different, but the concept is same. You start with specification, but rather than doing RTL, which works more for Boolean logic, you do schematic design, make sure it works for continuous time signals, do physical implementation, after physical implementation, GDS, which is your layout data, is generated, and then either you sell that to your customer or you fabricate it. Okay, let me see if there are questions which I can answer at this stage, if there are questions relevant to this. Otherwise, I'll continue. So there is a question of where is the EMIR flow? I'll talk about that in the one of the later sections. Okay, seems like there are no more questions. Let me continue. So there is a question whether memory IPs come under analog or they come under digital. It's an interesting question. Depends, right? So there are synthesizable memories also. Those are more like RTL, written from RTL. And then basically there are memories which are hard. Those come as hard IPs as well. And basically that so the memories are typically hard IPs, but there are some synthesizable memories also and those are what do you call soft IPs. Typically memories are sold as analog IP. So GDS is a layout format. Someone mentioned gate design scheme. It's basically a way of representing your design after place and out. It's just a format. Okay, so but the idea of that format is it represents your design after place and route. Okay. So we talked about IPs, right? Now a lot of most of the times IPs are not the end product. The end product is a system on a chip. Okay. The end product for you is a system on a chip. A system on a chip is basically you have multiple, let's say cell phone will be, or the cell phone system will be a system of chip. A system is that has all the needed analog, software, digital components, and hardware to work for a particular functionality, like cell phone. So you will have memory on a system on a chip. You will have some GPU, your clock generators, a lot of devices which will be clubbed together and fabricated on a single chip. And so that works like a system. It's a system. By system, I mean it does a particular system functionality, like say cell phone, and that is known as system of chip. So for designing a system of on chip, you may need memory IPs, which may be hard or analog. You might need, let's say, USB, which may be a hard IP, or you might need some other aspects, let's say PLL, which may be a hard IP. So basically, a system of chip person or a company which is working on system on chip will take multiple IPs, either from different companies. They will design some of their own IPs, some may be soft IPs, some may be hard IP. They'll club it together, make sure the functionality is working correctly, and then basically take it out to the market. So as you can understand, the flow will be then slightly different. It's a similar flow, but it will be slightly different. Okay. So how the flow will be different would be, you will start, of course, with specification. Specifications are there. You will then basically have design architecture. So based upon the architecture, you will decide, okay, what are the things I will need? Maybe I need these kind of IPs. Maybe I need ARM core. So I'll take a soft IP. I may need a memory. That may be a hard IP. I may need a PLL. That will be an analog IP. I will use all those IPs, then maybe my own internal IPs. I will do something known as SoC integration, where basically I will join all these IPs together, figure out how these should be connected, write the RTL code or for it. Maybe there'll be additional logic on the top of it. For example, when you are connecting a chip, let's say two blocks are needed. Maybe these two blocks should be connected in such a way should be an inverter in between. So this is known as glue logic which is present at the top level to connect these blocks, or basically some small logic which is present at the top level. You will then, once you have designed a chip, the rest of the steps would be similar. You will do verification, you will do synthesis, all the usual steps that we have seen before you do tape out or fabrication. Tape out is a term which is used, which basically when says you're done with everything you can do at software level or at the design level before you take it to the foundry. Tape out, as an earlier when chips used to be designed and the layout data used to be sent in tapes. Please be on mute during the session. So tape out is coming from earlier times when basically the layout information used to be sent on tapes, and those tapes are sent to the customer. Okay. So this is your SoC flow, or a system on a chip flow. As you can see, most of the steps are same, just that you are combining IP, so it's known as SoC integration rather than RTL design. Okay. Okay. Let me see if there are more questions, and then I will come back to what do you call this. Okay, so there is a question, what is the glue logic? I will talk about that, and then so basically, right, when you're designing a chip, for example, I'll use this space. Let's say I have these two IPs which need to be at the top level, but these IPs then need to be connected in some way. Sometimes their ports are directly connected. Sometimes maybe I need some additional logic to connect these. And this additional logic, I can write it in RTL. For example, let's say from here to here, it needs to be inverted before connected. So I will write this logic in RTL, and maybe some additional operation has to be done before these blocks can be connected. So all this glue or connections or the logic which is needed to do that connection is known as glue logic.
Excuse me, sir. Your screen is not visible.
Sorry, I don't know. Okay, let me share my screen again. Okay, can you see my screen now?
No, sir.
Yes, sir. Yes, sir. Now,
Okay, sure. Okay, so it's coming up, I guess. Okay, now it can be seen. Okay, let me then talk about glue logic. There was a question in it, but people, okay. Okay, so let's say you have a chip and there are multiple blocks on this chip. Okay, when you're doing at top level, these chips or these multiple blocks need to be connected with each other. Okay, so you will add some logic. Maybe it's just a wiring logic, output port connecting to input port here, or maybe some additional, let's say this needs to be inverted before it is connected here, or maybe some additional RTL code or logic needs to be added before it is connected here. So all this connectivity related logic, which is connecting it together or gluing it together, is known as glue logic. So it's basically logic sitting on the top which helps connect multiple blocks together. So in addition to when you have a chip, every chip will need a software, right? As in, let's say when you let's say you have a cell phone, on the top of the cell phone there is iOS which will be running, or Android which will be running, and that also has to be, if you are selling an end product, like you are a Samsung, you are Apple, you're selling that cell phone, you have to design the software for it as well. So every hardware, as a hardware product, will come with a software on the top of it. So, and basically there'll be a hardware team which we talked about, which will work on architecture, then RTL, then backend, it will work on that. At the similar level, there'll be software team which will be working on the software side, and there'll be joint activity in terms of architecture. Whatever you model on hardware, it needs to be modeled in the software side as well. Then there'll be system drivers which will be running on the top of it, which can run on the top of your chip. There'll be software prototypes, and then when the chip is fabricated, there'll be software bring up which will be done, which basically you will put your software on the chip, try to bring it up. Let's say it's a cell phone chip, you will try to bring it up, and then you'll do testing. So basically, for every hardware product or the product which actually ends up with the user, which with basically end consumer, a software product also needs to be designed, and that's why typically you will see software teams also in semiconductor companies, at least on the end product companies, and you will decide, as an architect will decide what needs to go into software, what needs to go into hardware. For example, let's say you want to do a multiplication operation. It can be made faster by maybe using a GPU. So software can be written so that when multiplication operation comes, it uses GPU. Okay, so all those things can be designed by architecture, and at the software level, that also decides what goes into hardware. And basically the flow, hardware software partitioning, what should be done in software, what should be done in the hardware, you try to find synergy between what my architecture should be, what the software should be, and how I can get best performance for the application I'm trying to design for my system on chip or my chip. Okay. So we also have you might have heard another term known as FPGA, which is field programmable gate arrays, versus ASIC, which is you are designing a chip for application specific chip. So far the flow we talked about was you design, you write RTL, synthesis, verify, and give it to the foundry for fabrication. Sometimes, or some when you are doing an initial product, you may not want to, you not want to give it to the foundry and design a chip, because you want to first make sure it works fine. For developing a chip in the foundry and getting it fabricated in the foundry is a very expensive process. So that makes sense when you're gonna design a large number of chips or large number of chips. For example, Apple knows it's gonna sell so many chips, so it's okay for Samsung. But if you're small, maybe you want to go the FPGA route, which is slightly expensive in terms of if you have less number of, as in, there are some pros and cons of doing that. So FPGA is something where you can design a particular logic, and rather than going to the foundry, you can put it on a board, which is a FPGA board, and directly put it on it without going to the foundry. So because you are directly putting it in a board which can be purchased in the market, and you just have to design your RTL, it's faster. You are able to design your product faster. But while in ASIC, you have to go to foundry, you have to make sure you have done place and route with respect to foundry. The ASIC processor is a little slower. Okay, but for designing a chip on ASIC, it's the costs, non-recurring engineering cost is high. You have to put a lot of engineers and a lot of expertise to design that you don't have to do on the FPGA side, because you directly can put it on the board. So the flow is also simpler on FPGA side, while on ASIC side it's complex. You have to make sure it work for the foundry you are using, all the design rule checks, manufacturing checks, which you have to do to make sure it complies with the foundry. Since this you are directly putting it on a board, these boards are expensive, so per unit cost is high. Okay, but it's okay if number of units. So that's why it's okay if you don't know how many units we are going to sell or how many units there are going to be. But here per unit cost is low, and that is low because you will usually sell a large number of units. So this high cost of engineering is kind of then distributed over multiple units. In FPGA, you may not be able to get the fastest performance on your for your devices. The best way to get faster performance is to have ASIC, so that you design it in your own way. But maybe you're not creating a super fast device. Maybe it's an IoT device which does not need that much performance or processing. Then you may be okay. Then the power consumption usually in FPGA is higher than an ASIC. That's why basically, if you think of cell phone, they mostly are ASIC devices. The size of the unit is also slightly higher. If you're designing it yourself, you are able to cram or make the best use of the space, which you may not be able to do in FPGA. So FPGA is basically where you're designing your RTL or a code and you're shipping that putting that on the board. Okay, that's what you're doing. But ASIC, you're designing it yourself, then you're asking foundry to manufacture which only works for that application and manufacture it. So typical FPGA, right? Board. This is talking about board, which is sold by Xilinx. There used to be Altera, which is now acquired by Intel, which will have logic like there'll be interconnected wires. There'll be connection matrix for connecting the wire. There'll be input-output ports. There'll be configurable logic blocks. These are like which can be configured to perform any logic. For example, let's say I want to design this circuit. There is AND gate, and then after that there is an OR gate. Right now, I can put my AND gate here. This is just an example. This will be more complex, and then connect this wire, which is already wiring thing, and put my OR gate here. Okay, so these two can be combined, and that basically makes the logic configurable. Okay, let me use, so you can put your AND gate here. You can put your OR gate here, and then use the existing wire to connect it. And then you can put it on the board. Once you put it on the board, it will do that functionality. You can reconfigure the board. Now you decide, okay, I don't want to do this logic. I want to put OR first and then AND later. You can modify the logic here. You can reconfigure the device and basically connect this to this the reverse way. So FPGA provide you a way to implement any functionality, okay, and connect them so they're configurable. Once you get a board, you can put function A on it, you can put function B on it, function C on it, and you can reconfigure it. After once they're configured, you can reconfigure it also. That's the advantage of FPGA. These are like in the field, you can program what circuit you want. There are some specific cases where you cannot configure some. There are like some space applications related FPGA also Xilinx provide, where you once program it, you cannot change it, but you can program it. So what is the FPGA flow then? How it is different from your normal ASIC flow? Okay. The only difference you will see is you will do a specification, all this you will do. But then once you're done with that, rather than taking it to the foundry to fabricate it, your FPGA tool, typically like Xilinx Vivado or Altera, similar Altera software, they will map whatever you have designed to a bit stream. Bit stream is nothing but a way to configure your board, and you will put that. Your software will configure your FPGA board. This is the FPGA board. It will configure based upon this bit stream to do the functionality you had designed here and put it on the board. So the only step is, rather than taking to the foundry, you are using let's say Xilinx you are working with, Xilinx software to program their particular board. And there are multiple kind of boards which exist, FPGA boards which exist. You will choose one which fits your functionality and has the kind of logic which you need. Sometimes some designs may need more logic, so you may need a bigger board, or you may need to connect 2 or 3 boards together. All those things can be done. But FPGA flow, rather than taking it to the foundry, you are configuring an FPGA board to the functionality, to do the functionality you want. And then, of course, once the board is there, you will do board level verification. Okay. So we talked about what are the various steps in the VLSI flow, what are the different kind of IPs, what is FPGA, what is SoC, how the flows differ from one another in this. Now we'll take a couple of minutes of break, and then so that basically if there are any questions I can answer, and then we'll continue with the next portion of the session. So there is a question: what is GPU? What comes under front end? What comes under back end? I will talk about that also as I go along. Where does the backend start? We'll take a 5-minute break. So it's 10:30 India time right now. We'll start at 10:35. If anyone wants to drink water, I'll also get water for myself, and then start the session again. So if you have any question, you just type it in the chat window, and then I will answer that. Don't need to raise your hand. I just type it in the chat window. So there are a couple of questions. SoC comes under FPGA or ASIC. SoC typically are ASICs. Can you share the PPTs? I will try to share the PPT. The recording definitely will be shared. From where do we do RISC-32 project? I think you can search on Google. I'm not definitely sure where do you do. I mean, you're asking which company. Linting I will define. So there is a question on lookup table. Okay, I won't be able to go into details of lookup table. We do have a free Telegram group for our users. Let me actually type that here in the chat window so that you can join and ask more, as in questions which are not part of this webinar, so that you can learn more from each other and from our community. Let me post that link in this particular window. Just a minute. Let me. So I just posted a link to our Telegram group. This is our free Telegram group for all the learners. You can ask questions there. There'll be people who can answer those questions. You can also help each other as well, and I will also try to answer those questions. So some specific questions. Does memory follow the general VLSI design flow? Memory typically are like follow the flow of analog IP and hard IP. There are questions on some backend topics. Sure, as in these are not specific to this session, so please post these questions on our Telegram group and I will try to help and answer. Okay. So there are questions on where backend starts, where front end starts, that also I'll talk about. So please join our Telegram group, and after the webinar, I will answer those specific questions once you post it on Telegram to answer it. Okay, so let's continue. Let's go back to the presentation. Let's go down details of each of these steps. So before I go, there was one question on where does front end lie and where does back end lie. So let me answer that, and then I will go into the rest of the session. So typically, right, as in when your design is not, as in wherever your design is not dependent upon technology, typically that is called as front end. So if you see here, the steps still here, where you're doing specification, architecture, RTL designing and linting, and verification, that is front end. So this starts going, this is your back end, timing analysis, place and route, fabrication, and all those things. This is your back end, and synthesis is somewhere in between, where basically you are doing mapping it to a technology, but you're taking RTL as an input and mapping it to a particular technology. So these steps are usually front end step, and then later steps are back end step. Okay, let me continue our session. Okay, so the first step, as we talked about in our flow, was specification. Okay, so what is a specification? Specification represents customer's requirement. Okay, what should be the function of this product? What should be the features of this product? For example, as a specification also talks about design elements, like what colors the device can be available if it's an iPhone. What will be the physical dimension of it? What should be the width? What should be the height? All those things. What should be the screen size? And all those things become part of your specification of the product which you are designing. So basically, this is either you imagine it, either you get it from the market, what market is looking for, and all these become part of what is known as your specification of the device. Okay, and once that is made clear, then you go to the next aspects of your design. So typically, this is captured in documents, Word, PDF, FrameMaker. There are some tools now also, although I'm not familiar with those tools, but you can also capture them this tool. But this is basically information. So typically best captured in your documents, PDF, docs, or slides, those kind of format, which is then used by people which are design architects. So once you have specifications, you design the architecture for that device. For example, you saw the specification for cell phone device. and based upon that an architecture is created. Okay, I will need a processor, I will need a GPU, I will need a memory, I will need power management unit, I will need maybe a GPU, which is graphical processing unit, which does a lot of multiplication and floating point of operation. I will maybe need a USB port to connect, I will need a charger. All this is then designed based upon the specification, because let's say you are creating a slow device, you don't need that fast a device, maybe you will not use GPU. GPU is typically used for multiplication, gaming, floating point operation maybe, and they are costly. So maybe if you're creating a middle end product or a low end product, you may not put it. So based upon whatever specification you want, architecture is decided. Okay. So let's talk about a specific, very small, basic example to explain this concept. So let's say you're designing a cell phone, right? For a cell phone, maybe you need to the one of the feature of the phone, which is said in specification, is that let's say your screen turns off after a certain time. Okay, so basically, let's say you're running at a particular clock in the chip, and your screen should turn off, let's say, after a certain time. Then architecture will decide, okay, I will need a counter there, because I will need to time it, maybe that like clock is, I need to count 4 times. After that, this time is over and screen needs to be turned off. So this is your specification, and from the specification you derive, okay, I will need a counter. Similarly, let's say this is just a simple example. For complex devices, you may say, okay, I will need this much memory, or I will need one fast clock for a high frequency operation, maybe I will need one slow clock. So all these decisions are taken by your chip architect during that time. Architectures, there are basically tools where you can capture architectural information, and you can do architectural exploration. By exploration, I mean, for example, you want to check whether, let's say, 10 by 10 memory would be good for me, or when 20 by 10 memory would be good for me, for my performance needs, for how fast I want to run. You need to determine that without even coding it, without doing any coding or starting any RTL coding. Let's say you want to figure those things out. There are design tools which allow you to do that, which is known as architectural exploration tool. These typically are coded in System C language, which is a subset of your C or C language, and it's based what is known as TLM based, which is transaction level modeling based. There are a couple of tools available, at least which I am aware of. There are maybe more, Synopsys and Mentor. There is Platform Architect. There is Virtual Prototyping Tool. And what it does is, it's not implementing your real design. For example, let's say you have a FIFO. Okay, FIFO means you are writing something in the memory and reading that from the memory, first in, first out. So you're reading that kind of data. Now, if you look at real design or silicon, you will have so many ports, so many clocks, you will have a RAM, you will have all this detailed information, which will actually be designed later on. But at a high level, in early architectural exploration, these tools will provide you libraries where basically you can say, do this at a very high abstract level. You can just say, okay, I need a FIFO, which is the size this by this. You don't need to design everything. And you can check, okay, when I put the data here or read the data here, what kind of performance I am getting for my chip. Okay, so these design tools help you use certain libraries and components at a higher abstraction level. You can directly instantiate a FIFO and those kind of things, and run performance estimation or architectural exploration on what is known as transaction level based models. So these models are which can do transaction, like put something in FIFO, read something from FIFO, not at the signal level, like you will turn read to be high, then memory data will be read, but at a higher abstraction level, which is known as transaction level modeling. And this is typically done in System C. and that you can use to explore the design. So for architectural exploration, there are certain design tools which exist which allow you to do that. Okay, let me see if there is any question, and then I will continue. So someone is asking how long is the presentation? I think it will take still 1.5 hours more, but the recordings will be available. So so don't worry, you can check the recordings later also if you're not able to join us for the full session. Okay. Then once you have designed your architecture, as I said, you will go into RTL coding, analyzing your RTL, designing your RTL. Okay. So what is RTL coding? Okay, RTL coding is basically RTL or register transfer level is basically where you will design your circuit or design your logic, synchronous logic, in terms of flops and combinational and logical equations. Okay, so typically you will design what will be flops in my design, what will be the combinational logic in my design, and you will write those in typical languages which there are. There are two languages, HDL languages. Typically two are mostly used. One is Verilog and another is VHDL. Verilog is most common. VHDL is slightly becoming less and less used. There is also SystemVerilog, which is an advancement over Verilog, which is also used. So here you will write your functionality of the design in these hardware description languages, where you will write in terms of flops, combinational logic, logic couple operations, and that is what is known as RTL design. Okay, and you will write those in hardware description languages. So typically HDL, RTL is coded in hardware description languages, Verilog, VHDL, SystemVerilog. And if you are trying to get into a job which is related to RTL designs, at least one Verilog you should know, okay, or VHDL you should know. This captures the HDL languages, captures the design functionality. What is the function you're doing? Maybe you're designing a state machine, it will capture that. Our counter example, which we saw, right? You will design that using these languages. This is typically done in text editors. There are some companies, for example, what I've seen at Intel is you can write a snippet of the code or functionality in doc format document, and it will convert that into RTL. So these kind of things also exist, but typically you will write these in text editors, which are like Emacs, VI, Vim, and edit, as in there are multiple text editors which exist. So let's come back to our counter example. So at the architecture level, we had decided that we need a counter, okay, which needs to count like this, 0, 0, 0, 1, like this, and so on. We need to design this counter. Now, in RTL languages, I have taken the Verilog example. You will design this counter, okay? So this is the language, Verilog, how you can design this counter. So you will have module counter. You will basically write the functionality, which is a flop here. When does it go up? When does it go down? All that functionality you will decide. The advantage of writing this in this language is, now let's say you need counter at 2 places in your design, not just one, or maybe 100 places. You can directly reuse this code on all those 100 places rather than writing it again and again. So RTL design provides that capability, and which helps increase usability, reusability, and reduce the effort in this way. So you thought about, okay, at architecture level, I need a counter. Then this is how you will code in RTL design using the Verilog language, that counter. VHDL can be used, SystemVerilog can be used, but typically these are the languages which are used to design your RTL. Now, typically designs will be more complex. Okay, you won't be just designing a simple counter. There will be complex design. We think of cell phone design, iPhone. It's a very complex design. So how will you design so much RTLs? How will you write so much RTL? So this is typically done by divide and conquer strategy. You will break down your design, and this is typically for hardware, for any, even for software product, you will break down, you will modularize your architecture and design into what various functionality. Each of those functionality or system will be smaller parts. They will be coded separately. Some of them may already exist. Like, for example, you have already designed the counter. You can use that counter at other places as well. No, you don't need to write it again and again. You can reuse it. Similarly, let's say your cell phone needs something, let's say needs a memory, right? You will not design it again. You might already have an IP which you can reuse. So as in once you modularize the design, you will break it down into a smaller part, smaller functionality, and some of the functionality may already exist, you will reuse. Whatever functionality does not exist, of course, you will have to then write a new RTL code for it. So, but basically for all these big chips, you need RTL or this RTL design, but you break it down by divide and conquer. So, and figure out what portions I already have and what I don't. Whatever you don't, you code again. People work together on and code again. So as I said, right, it's not one person who is designing that chip. There are thousands of people who are working on various parts of it, of this RTL to make it. So now you have designed your RTL. How do you write your RTL? So what there are two ways to write your RTL. Okay, one is known as behavioral modeling, which is basically what the behavior of RTL is, and second is a model you write in a what we said was more closer to design, which is flop and combination logic. That is non-behavioral coding or synthesizable coding. So for example, you can just say X is equal to A times B as a behavioral code that basically this is a multiplication operator. But multiplication is not directly synthesizable. So you will have to create the full logic for it in terms of flops and gates. Let's say you will do carry, you will do each multiplication, all that has to be specified to design it. As I'm taking an example, these days synthesis tool can also synthesize multiple, but just to take an example, that real RTL coding, which can be synthesizable, will be more detailed, but behavioral coding can be at a slightly higher abstraction level. And typically both of these are done so that you can verify, okay, what my behavioral model is giving output versus my real RTL, which is giving output, and then you can compare and see it's working correctly or not. Now there was a question on what is RTL linting. Okay, so RTL linting is once you have written your RTL, you want to do quick checks on that RTL. Okay, what are these quick checks? Maybe like maybe some port you made a typo and did not connect. For example, let's say this was a design, this output port was O1, but you connected it O. Let's say you connected a wire O, and you forgot to connect it. Okay, now these are simple mistakes which can be caught very easily without needing to run any verification, and that is the role of the lint tool. It catches early issues in your design. It can catch just by reading the RTL based upon the rules or policies you have defined. Okay, for example, you have told, okay, that whenever the ports are not connected, show me that problem in my design. So that is the rule that you want to enable this rule. And then your linting tool will check that rule and flag if there are design problems you can fix. So linting is the fastest way to identify bugs, problems, issues in the design. There are multiple companies which provide linting tool. For example, there is Ascent Lint from Real Intent. Then there is Spyglass Lint from Synopsys, and I think there is some lint tool from Mentor as well. But basically, linting is just looking at your RTL, checking if there are issues in their RTL without running any simulation or any verification. Linting tool is able to do a lot of verification by just reading your RTL, by taking your RTL as an input. And this is also done in software. For example, let's say you're running Python or you're running in software languages. Some of the checks can be done just by looking at the code. Like if you have used Eclipse, it will start telling you some of the issues in your code by just at the time when you're writing it. Those are the kind of things linting tool can do. It can find issues in your design which are like basic issues, but it can do it very, very fast. That's the value of linting. Okay, let me see if there are more questions, and then I will go to the next topic. So the question is, what is divide and conquer? Divide and conquer is basically you, let's say you're designing a cell phone, right? As in it's a big functionality. You will divide that into smaller parts. And those smaller parts, let's say maybe counter, maybe what do you call maybe counter, maybe other functionality, memory. So basically, you're dividing your full chip into smaller logic, and that is what you will check. LUT is a lookup table. I'm not going into details of that. I think this question has been asked multiple times, and I will cover. I will cover CDC and RDC check. I know there is a question on that. I will cover that in verification. Okay, so we talked about how do you start designing, specification, then there is architecture, and you do RTL design and modeling. Now we'll go into next step, which is verification of this RTL. So you have written some RTL. How do you verify that RTL? What are the various techniques to verify it? What are the various tools to verify it? Verification basically means making sure that whatever you have implemented now in RTL matches whatever your requirements or specifications. So during specifications side, you created this document. This is what I want to do. Okay, now you have written that RTL corresponding to it. Now you're going to verify whether this is working the same way or not. There are multiple ways to verify, and each one has its own value, and a mix of these methods are used to verify your chips. One is known as simulation, basically where you simulate or basically try simulation tools run your RTL code. We'll talk about that. There are static ways. In simulation, you will give test benches. Static ways work without any test benches. If you think of linked, which we talked about, is also a verification tool, which without just by giving RTL no test benches, it is able to find some issues. Then there is formal verification, there is emulation, there is assertion verification, there is CDC, and so on. So we'll talk about these two. But basically in this, you're verifying whatever your design is working correctly or not. Okay. So let's basic first verification, which is most common, is simulation, or also known as dynamic verification. It is known as dynamic verification because you are creating a test bench, and dynamically on that, based on that test bench, you are verifying your design. So typical step is create a test bench. So test bench is nothing but basically let's say you have counter. For counter, you will initiate something, then give some input signals, then you will observe the output signal, all that operation, what input signals will be given, what should be the expected value of output. All those things are coded in plain in Verilog language itself in your test bench, or it can be VHDL. But test bench is basically which is putting your device under test and verifying what you have implemented. And this is typically done in the same languages in your designing. So you will create a test bench, you will instantiate the design in the test bench, you will provide stimuli that you will give some values on the input, you will trigger the clock. Once all this is done, you will compile that in a test bench, compile that and run it in a simulator. There are a lot of simulators, as each of the company have a simulator. Synopsys has VCS, Cadence I think has an NCSIM, Mentor has Questa. Each of the big companies provide a simulator. There are simulators as well, open source like Verilog, and those can read in your RTL and test bench and verify the logic is working as required after running the simulator. How do you make sure it's working as intended? You observe the output signal. For example, for counter, you will see, okay, what is the count value, which is you are giving as an output, you will observe that value. Okay. So for our counter, a simple test bench would look like you will create a module named counter test bench. You will initially put clock on 0 and you'll say, okay, after this much time clock should recirculate, it will create this kind of behavior. Then you will instantiate your test or monitor what is the value of the output. You will instantiate your counter in this design. And here you have instantiated a counter, and you will, to its input, you will give multiple values and observe the output values and see if its value is as per you had expected it. Okay. And this is all coded up into Verilog language right now, as in this is Verilog test bench. But as in I'm not going into detail of how to code it, but basically you are instantiating your module or unit which you want to test, you will give it some stimuli, and then you will observe the output, and that is what is done in simulation or dynamic verification. Okay, so your simulation or dynamic verification is you have a block, you will get some stimuli, and then you will observe output. So of course your output is a function of what stimuli you give. Okay, let's say it was a counter and you had designed the counter both for going up and going down. Okay, and depending upon let's say up down signal as which is an input, it goes up or goes down. If you only feed 1, that means it only goes up and never feed 0, then you have not tested that functionality. Okay, so testing of functionality in simulation or in dynamic verification is a function of what inputs you give. So if you have given all the inputs, then you have verified all the functionality, but if you have not given all the inputs, you have not verified all the functionality. So it's dependent upon what inputs you give. So it's limited by what input you can give. And typically to ensure that you have given all the inputs, there are people ensure that there is something called coverage, that you have covered all the inputs, all the values, and usually typically designs will have 99.99% coverage to ensure everything has been verified. Okay. So simulation, once you do simulation, your simulation waveforms will look something like this. You can check even in the waveform view, values counter is increasing 1 by 1, values are as you expected it to be. Now there is also another term known as emulation. Okay, so when you're running simulation, you are running simulator tool which is reading the RTL and test bench and verifying it, processing it, and verifying it. So it runs purely on your software. On your, like if you're running on laptop, it's running on your laptop. You give RTL, you give software, and it will verify. That is very slow. Sometimes that for big designs, let's say cell phone, iPhone device, you want to simulate it, it can be very slow. It can be made faster if you run it on an actual hardware. Okay, so and that is known as emulation, where basically whatever RTL you have written, and typically these are either FPGA board or specific board created by companies like Synopsys and Mentor, where your RTL is ported on a board, and basically this board is connected to your software, which is a simulator, and you rather than testing everything on software, the code actually now basically the logic only runs on hardware, but the values are tested on the software. So emulation, basically the actual processing running is happening on a particular hardware which implements your for design functionality, and that you verify it. So it runs faster and it's able to handle large size chips. Okay. So in terms of verification, they are verifying the same thing. Emulation is just a way of running it on hardware to make it run faster and handle big size designs. Then static verification. So far we talked about dynamic verification, where you're writing test bench, and the limitation is it will basically whatever you run, whatever input you give, your results will be similar to that, and it applies both simulation and emulation. As I said in the counter example, that if counter can do both up counting and down counting, but you only change up counting signal, then verification will be limited to that. Static verification is slightly different. Static verification is the process of verifying the design without giving any test bench, without giving any stimuli. It just verifies some predefined rules. So the advantage you get is it allows you to verify without any stimulus, without any writing test benches. And that is known as static verification. Advantage it gives is you don't have to worry about coverage. Okay, because if your rules are good enough, without writing any test benches, it will verify each and everything about your design. Okay, versus dynamic verification, where you have to write test benches, and whatever test bench you write, only that thing is verified. So a lot of applications where static verification is used, for example, clock domain crossing, formal static timing analysis, some design rule checking, these are static applications where you don't write any test benches, but it verifies based upon your RTL, which is good. Lint is also a static application. So the advantage you get from static is that you are able to verify each and everything, versus dynamic or simulation, whatever test bench you have written, only that thing is verified. But of course, static has its own problems. So mix of both the techniques are used. Both dynamic simulation is also used some places. Static is used where it's good. Then there is formal verification. Formal verification is mathematically analyzing the behavior of your design, rather than for a particular value which you have written in the test bench. Okay. So for example, in case of counter, tool can directly read RTL of the counter and formally verify, yes, it's increasing the value each cycle by mathematically proving it. It's like proving, convert that design into mathematical Boolean equations and prove or disprove that it is not increasing every cycle or not. Okay, so formal verification is another method. The limitation with formal verification is it cannot work on large designs. It can only work on very small designs. But once it works, you don't have to worry about coverage. It will 100% prove everything it can using formal verification. So as with each engineering solution, there are challenges and advantages of each solution, and depending upon which fits, a chip team will use each of them. So all these methods are used. Static verification is used, formal verification is used, simulation is used, dynamic verification is used, depending upon which works best. And basically you will learn along the way that which works best for each of these cases. Okay. Then there is assertion-based verification. Assertion-based verification is you can write certain properties of your design, certain things about your design. For example, in this case, request gets acknowledgement before request is changed again. So when request, this is the property of the design. This is how the design should behave. So when request changes, before another change, acknowledgement should go high. Okay, and basically you can code this property or this behavior of the design in terms of what is known as assertions in SystemVerilog languages, and you can tell the tool, okay, when request is high, before next request goes high, acknowledge should have been high previously. That kind of thing you can code in RTL languages, verification languages actually, known as SystemVerilog. One of the languages, SystemVerilog. And these are properties of your design, assertions on your design. This is what is going to happen on my design. And this then can be either verified formally, like formal verification tool can take this assertion and verify and make sure there is no counterexample that this behavior is always followed. But if this behavior is sometimes not followed, it will tell you, okay, at this situation, it will not be followed. Or when your simulation or test bench is running, if this situation is failing, that also assertion can flag. Assertion is typically basically a property on your design which you can code and which can be used in your design. Then static verification. Okay, so one of the common application of static verification is STA, which we'll talk about later, and clock domain crossing analysis. And clock domain crossing analysis is analysis of clocks when the asynchronous clocks are there. Okay. So synchronous clocks are clocks where basically events happen at a fixed phase relationship, while asynchronous clocks are clock where basically events don't happen in a fixed phase relationship. What we mean by that is, if you know edge of the one of the clock, the edge of the other clock will happen precisely or deterministically, then they are synchronous clocks. It's not dependent upon frequency. You can have different frequencies clock. Let's say one is divided by another. Still they can be synchronous. Or you can have same frequency clocks, but still they can be asynchronous. This is driven from the physics that you have different clock generator. It's not possible for them to be by default synchronous, and you cannot have a fixed phase relationship between them. So if you cannot have a fixed phase relationship between them, you will have to do specific design known as clock domain crossing design of those blocks to avoid metastability in the design. We do have a separate course on CDC and STA, but at a high level, I'm covering here. So if you have more than one clock domain, which can be asynchronous to each other, you can have possibility of metastability in the design. And in order to avoid that metastability, designers put special structures like synchronizers in place. And your CDC verification tool verifies those correct structures are correctly placed, they are behaving correctly. That is done by your CDC verification tool. Again, these verification tools are static in nature. There are no test benches which are given. And based upon just your RTL and other inputs, it's able to verify whether you have CDC issues in your design or not. So between synchronous clocks, you use another static tool, which is STA, static timing analysis. Between async clocks, you will use CDC verification tools. This is done during RTL. CDC tools are run during RTL stage itself, or just after during RTL verification in parallel or after that. Then once you have done verification by using whatever means you wanted to use, then you start going towards backend. And what I mean by backend, you start making it closer to a particular technology. And during the next step for that is logic synthesis. You will do DFT test. I'll talk about that, some low power implementation and equivalence checking stuff. So this is where you start going towards backend kind of job role. So let me check if there are any more questions. Otherwise, I'll continue. Okay. Okay, looks like my slide got closed. Let me open it again. Okay, it's there. Let me share my screen again. Okay, seems like no more questions. I will continue with the next step. Let me confirm you're able to see my screen. Okay, it's coming up. There is a question. The verification discussed now is pre-silicon verification. Yes. The first part of the webinar you can look up later. What is behavioral coding? I covered that earlier. Behavioral coding is you are writing at a slightly higher abstraction level. For example, let's say multiplier. Maybe you're just in behavioral coding. You just say A cross B, and then basically sorry. So you might just say A cross B in behavioral coding, but maybe you synthesize it closer to flops and combination logic in your actual RTL coding. So let me go to the next step, which is logic synthesis. So in logics, basically as you are writing your design, let me confirm you're able to see my screen. Just yeah. So there are different abstraction layers you will write your code. Okay, behavioral code is when you're writing at a higher abstraction level. You're saying function, let's say a and b, and function is a multiplied by b, or maybe a plus b plus c plus d, something like that. So you're writing at a higher abstraction level. RTL is when you're writing at a lower abstraction level, how it will look in terms of flops, deflops, and combinational logic. Now, synthesis is when you start going from RTL to a lower level, which is more in forms of gates, which is present in your library or which will be present in your silicon. And so from RTL to you go to a lower technology specific level. RTL is higher abstraction level, but you go to logic level, abstraction level. And this is done by your logic synthesis. Okay, so your logic synthesis, there are tools to do logic synthesis, which will convert your RTL level language description to gate level description, and OR gates, flip-flops, other kind of flip-flops, XOR gate, whatever is present in the library. This library, what gates are available, how many inputs, how many outputs is typically provided by your foundry. Let's say TSMC may have a library which will tell, okay, I have 2 input AND gates, I have 4 input AND gates, and all those things. And synthesis tool will take that as an input, your library, and convert your RTL to mapping to those gates, and that is known as synthesis. So what happens is, let's say you have this RTL, which is high level description, which is let's say Verilog description. Your synthesis tool will convert that into a generic AND OR gate kind of Boolean. Then based upon the library information you have given, it will map to specific library, target technology. Let's say from TSMC, you have got 45 nanometer library. Then this general Boolean operations and OR gate will map to that specific library. So this happens all during synthesis time. You start RTL, and then the output is your AND OR gate based upon logic. Again, this netlist, this is also known as netlist, which is usually Verilog format, but as in if you are running FPGAs, Xilinx may have specific format, but it mapped to a specific technology. In case of FPGA, specific board which supports it. So typical synthesis flow will need your RTL files where you have coded your RTL in Verilog. You will need libraries. As I said, these libraries will be what you are getting from a particular vendor like TSMC, Samsung, whatever the cells they have. You will define your environment. You will basically multiple commands in the tool. You will tell, okay, what is the load, what is the constraint, what is the clock, what is the frequency of those clocks. All these inputs will be given. Based upon that input, tool will convert your RTL, which is this, to a logic and OR gate based logic, which is again written in Verilog format. This is also Verilog. In gate level, this is also Verilog, but the level of abstraction is different. Here you're writing at a very high level. Here it will be in the form of AND and OR gates and flops from the library. So inputs to the synthesis are your RTL, which you have written, timing constraints, which tells you what is the load on the port, what is the frequency of the clocks, those kind of things. Then library, what are library provided by your foundry. Physical library sometimes needed, it's an optional thing, and based upon that it will create a synthesized design. So this is design compiler flow. Since nowadays tool also support making your synthesis better, taking physical information like physically I will place these 2 blocks together or not, because of my limitations or my advantages I will get in physical design. These days tool also provide where you can give physical information in terms of place, routing, power related information to create a better synthesized design. But these are optional, as in earlier technologies did not use that, but now it's more collaborative. So one of the tools, design compiler, and other synthesis tool also support it. Kind of constraints you will give, what is the load on the output port, what is the frequency of the clock, what under what operating conditions I will be running. Operating conditions are like what will be my temperature, what will be my voltage, those kind of things. These are basically based upon that your correct cell from the library is picked and then synthesized. Typical synthesis tools, you have Synopsys Design Compiler, then there is RTL Compiler from Cadence. I think there is an open source synthesis tool known as Yosis. I've not used it myself, but there is some. So for each of these things, there are some freeware or open source tools which exist. They are of course not as advanced as commercial tools, but for like learning, it can give good results. Now you have synthesized your design. Okay, so you had written RTL, and your synthesis tool read that RTL and has created a gate and a flop implementation of that. So it has created a gate level information. Now, how do you know that whatever I had written in this RTL and whatever is in the gate level here are equal? How do I tell that? As in whether the synthesis tool has done its job correctly or not? How do you know? This is verified using something called equivalence checking, and there are equivalence checking tools for that. So what equivalence checking tool does is it verifies whatever has been synthesized by your synthesis tool is equal to what was written on the RTL tool. So there are no, let's say if there are bugs in the tool, it can have created a wrong logic. Okay? Equivalence checking tool, again, it's a static verification tool, or also known as formal verification tool. The equivalence checking, equivalence is checking equal between RTL and gate level netlist. How does it check? Okay, so it breaks the design into flops and checks what is the logic between those flops and check what is the Boolean equation for that logic. So in this, the Boolean equation for this, maybe let's say this is X, this is Y. Between X and X is equal to Y. Between X and Y, if there is a buffer. Now let's say there is a modified version of the design which does this. Here this is X and this is Y. Between n x, so X goes here, it goes inverted, then it goes inverted here. Here also the equation is X is equal to Y. Since mathematically both of these functions between the flops are same, equivalence tool will say, okay, yeah, this is correct because function is same. Similarly, so it will break the design into multiple parts. So you have this design, it will break the design into flop to flop, input to flop, or flop to output. This part, this part, this part. For each of these parts, it will create a Boolean equation, both RTL level and gate level. It will create a Boolean equation. Let's say this is equation 1. This is equation 2. And it will verify that these two equations are
Sir, you are muted.
sorry, when did I go on mute? Were you able to hear? Can you hear me
No,
now?
sir, just now you are muted. It's okay.
Just 2 minutes back, nothing. Yeah.
Okay, I don't know, it happens automatically. Okay, so let me come, let me see if you are able to see my screen. Yeah, you are able to. Okay, so let me come back. So basically, your design is broken down into 3 kinds of parts. One is input to flops, flop to flop, and flop to output. And let's say this is gate level representation. This is RTL level representation. For each of these portions, it will convert those into Boolean equations, and it will verify those equations are equal. So this equation is equal to this logic, this equation is equal to this logic, and equation are equal. So in this case, you see it when it goes from x to y, this is x, this is y. When it goes to x to y, there is a buffer. So equation is just a buffer, x is equal to y. Here, for the same path, it will check when it goes from x to y, the equation is first inversion and then another inversion, which is same as saying these two nets are equal, so x is equal to y. So it will say, yeah, this logic is same, doing the same functionality, even though it is implemented differently, but it's doing the same functionality. So these are equivalent. So y verification is done. That it's the same logic. Similarly, it will say check here. Okay, let's say this is A, this is B, and this is NAND of A and B. Okay, so A, B, NAND. Here it will check, okay, what is this? Is it the same functionality? It will say, okay, NOT of A, and this is NOT of B, and AND of that. Is it the same functionality or not? Okay, this is actually OR. Yeah, so OR of A and B. Is it the same functionality or not? If this is the same functionality, which is the case, then we'll say, okay, RTL and gate, even the logic which is written is RTL, the Boolean equation for that, and the logic which is written at the gate level, the Boolean equation for that is same. Now, in order to do that, it breaks it down into three parts, which I said, 1, 2, 3, input to flop, flop to flop, and flop to output, and verifies each of these equations, compare between RTL and gate individually. And if they are doing the same functionality, it says, okay, equivalence checking is clean. If somewhere it fails, it will say, okay, equivalence checking is not good, and point out to you, okay, here it is not matching. Why it is important is because synthesis tool may make mistakes or may have some bugs, then it will be caught here. It is very important in chip design flow to catch these kind of mistakes. So because it's a complex and expensive if you have a design failure at the silicon level. So this is how equivalence checking tool works. And if you see, there are no test bench which is given to it. So it basically verifies it statically or formally, and is a formal verification without giving any test bench. And this is used very widely. Every synthesis tools output is used. It does not only apply to synthesis, it can also apply to other areas. For example, you use place and route tool to modify the design, then also you can check equivalence. So equivalence checking generally applies to a lot of places, but this is the basic concept. It basically converts the design into inputs to flop, flop to flop, flop to output. It creates equation for each of this logic. Once these equations are created, it is verified, okay, this is equal to this is equal to these, and this is equal to this. Each of these equations is verified, and that is how equivalence checking tool works. So we took a simpler example, but this in general the logic will be very complex, and that is how it is verified. The tools for equivalence checking, there is Synopsys formality, there is from Cadence LEC, which actually verify the synthesis output matches RTL using the equivalence checking concept we talked about, and they do it. The next thing which we do to ensure the chip does not fail and you can identify chip is failing or not failing at the hardware level is known as testing. So in testing, you check whether a particular piece of hardware is working correctly or not. If it's not working correctly, you reject that chip. If it's working correctly, you pass it and ship it to the customer. Now, in order to test these chips reliably, there is a technique which is used known as DFT, design for test. You design your chips in such a way so that they can be better tested at the hardware level, silicon level, and that is known as DFT, design for test, and we'll talk about that. Why do you need to test that? Because when you are manufacturing a chip, there are unintended problems which can come in the chip, or also known as defects which can come in the chip. These are basically differences, physical differences between hardware implementation and intended design. For example, when you're manufacturing, sometimes some nets, because just fabrication is not 100%, there can be some nets which can be unintendedly connected, some opens, may stay there unintentionally, and that can cause chip to fail or not work correctly. You don't want to ship these chips to your customer. Apple does not want to give a phone which has this kind of defect. So, but how do you make sure these defects are not there? You test your chips. And in order to test your chips, you test your chips better, you do something called DFT, which is you add additional logic in the design so that they can be better tested, or this is also known as DFT or designing for test, design for test. So what are the things you do? Okay, let me talk about that. So there is a one particular method which is very popular to design these chips is you basically make your chips in such a way so that you can put any values on any flops, and then you can test whether that flop has taken that value. Okay, for example, let's say this is a flop. Okay, now for some reason, let's say Q pin of this flop is directly connected to VDD. Okay, let's say there was a chip problem, there was a VDD rail which was going on, then this signal was there, and unintentionally, like we saw here, they got connected. Now this signal then will always be 1. You can never have a 0 value on this because it is directly connected to high voltage. Now, since it's directly connected to high voltage, it can now not have a value 0, and that will cause design to fail. But how do you test it that it cannot have a value 0? It is not possible. So you only way to test this is you try to force a value 0 in this, and then check the value whether you are getting a value 0 or not. If you're not getting a value 0 and always getting 1, even though you tried to force 0, that means there is some problem. This pin is always stuck at 1. It's not changing its value from 1. Now, in order to force a value, this flop may be somewhere deep inside the chip. For example, this is this flop. This flop may be somewhere deep in the chip. How do you force a value on this? So this is, let's say, somewhere deep here. And how do you force a value on this? In order to force a value somewhere deep here, what you do is you create a chain of all the flops in your design, okay? Because you can only put some values through input port, okay? But you can create a chain. This chain does nothing but passes value from the input port to a particular point in the design. And let's say you want to force value 1 on this now, or force value actually 0 on this now. You will give 0 as an input to the chain. This will go to this flop, then will go to here and try to force a value 0. Now to see whether this 0 was forced or not, it will take output from here and put it to an output pin. So using chains, these are known as scan chains, you can force a particular value on a particular net or a flop in the design and then observe that value on the output port. Because on a chip, you will only have most of access to input and output ports after it's fabricated. But if you can create this chain, you can force any value anywhere, observe that value anywhere, and that will allow you to test whether chip is failing, whether a particular flop always is connected to VDD, mistakenly connected to 0 or stuck at certain value. This way you can test it out. And this allows you to test your chip very rigorously after it's fabricated. So this is very commonly used, and this is also known as DFT or design for test. You hook your chip into scan chains where you can push in certain values, take out certain values, and that is what is done to ensure that. And this is after synthesis. How it is done is you convert each of your flop, which was done after synthesis, modify that flop from a normal flop to what you call a scan flop. So what will be a scan flop? Scan flop in normal operation will take values from input data and give it to the output. But during scan operation, it will take value from scan input and give it to a scan input. So you have added additional ports on that flop in addition to normal flop. So normally you will have just input and output on a flop. But in scan, you have added additional scan input and scan output. Now these additional scan input and scan output then can be connected in this chain and can be used to specific value on certain point and observe that specific value on the output. So this is known as DFT scan chain insertion. This is done after synthesis or for your design. Okay. This then, which we already talked about, this allows you to test whether a certain pin can be tested for a constant 0 or 1 value or not. Okay. So basically during synthesis, after synthesis, you will do something called scan insertion, which will convert a flop to a scan flop, connect them into a chain, and you will have a scan, what you call scan inserted netlist. And then later on, at the tester level, when your chip is fabricated, you can use this scan information. You will apply a pattern, check whether you're getting desired results or not, and based upon that, you can discard the chip or accept the chip for your when it's passing the testing or not. So scan insertion right at this stage helps you improve reliability of your chip. Why do you want to improve reliability? Because Apple does not want to send phones to its customer, out of which let's say 20% of those fail. So they want to do as much testing as possible before they give it to the customer, because that is how the reliability of the device can be improved. So DFT is one by which you are able to improve testability and reliability of your devices. So after DFT is done, there are, let's say, multiple chips also which you can connect together. This is known as JTAG scan chains. So DFT you do for inside of the chip, but let's say multiple chips need to be connected for testing. You can use JTAG scan chain, boundary scan. There are multiple techniques which are used to do that. We have a DFT course which goes into details of that. Here I'm covering at a high level because the focus of this session is on the design flow. Then there is built-in self-test, basically where chips can test themselves. This is typically used for RAM or some of the testing internally. This makes testing less expensive because the test is very expensive and testing time is very expensive. So some of the testing you can do within the chip itself. It can automatically check whether that particular logic is working correctly or not. This is typically done for RAMs, built-in self-test. Then, yeah, basically online based, offline based, there are multiple kind of based. There can be BIST for memory. BIST is built-in self-test for logic of the design. Typically, I've seen mostly it's being done for memory, but there are logic BIST also, which is done. Then for analog circuit, the testing is slightly different. For digital circuit, we did DFT, I did flops. Basically, the analog circuit, once it's fabricated, you test every specification which is there in the data sheet. You check what is the intended time. Since it's a continuous signal, you have to check continuous behavior and waveforms of those responses at the input. For example, analog to digital converter, digital to analog converter. Analog testing is done slightly differently and does not use that similar kind of DFT, but also that has to be done, and there are special care which is done during the synthesis stage to ensure, or in this case, the schematic capture stage to do that. So tools which are used for testing, Synopsys has TestMax, there is Descent from Mentor, then there is DFT tool from Cadence as well. So all these tools you can search as an, don't need to remember the name, but just to give you an idea, there are multiple tools which exist for testing as well. The next aspect is power aspect, which is again a very critical design parameter. In addition to your area and speed, power is also important criteria. And chip typically consume power when there are signal switching happening in the design. Like it can be like a dynamic power, which is when basically either when you're, let's say this is an inverter, when input is at logic 0, output will change from 0 to 1. That means this capacitance will charge. And this is the switching, because input is changing from 1 to output is changing from 0 to 1, so some switching or some change is happening. Some power consumed for that to charge and discharge output capacitance, and that is known as dynamic power. Similarly, when input is going from 0 to 1, the output capacitance will discharge, and that will also consume power again to charge or discharge the output capacitor. Again, when the switching activity is happening, that the power which is consumed is known as dynamic power. And a dynamic power is a function of what is the frequency in the design, what is the load capacitance, what is the voltage level which is used. Since it's a function of all these three factors, people typically want to reduce power consumption of your devices, and they modify or change these factors in multiple methods. We won't go into details of those methods, just a high level overview to reduce power. So one of the methods, for example, is it's dependent upon the frequency. So what if you can reduce the frequency? You can change the frequency. When can you change the frequency? When basically there is no function happening here, can you turn off the clock? Which is done by adding a clock gating, that when no operation is happening here, I will just turn off the clock so that F becomes 0, and my dynamic power consumption at that point of time will become 0. So that is one of the methods which is used. Or let's say it's dependent upon VDD. My voltage basically is high, then the power consumption is high. Can I reduce the voltage? So for some of the devices, I will reduce the voltage. Rather than using 1.2, I will say use 1.0, I will use 0.9. And since the power consumption is directly proportional to square of the voltage, it will reduce my power consumption. Of course, when you reduce the voltage, it increases the delay of the gates, because the current volt is directly proportional to voltage, so current will be lesser, so your delay will increase. But if you're still able to meet your chip goals and frequency you want to run, or you can reduce power by reducing the voltage and still able to meet the frequency goals, then maybe it's okay, as in even though some of the parts of the logic is running slower than the maximum capacity, but you reduce power. So there is a trade-off, but this is another method by which you can reduce the power which is consumed in devices. So again, I'm not going into detail. There are specific power related courses which we have on our website. If you are interested in details of that, you can take that. Here we are just covering the high level flow. Then there are multiple tools used for power. There are static verification tools for power like Synopsys LP. There is Cadence Gold, Mentor Questa. Then there are tools to estimate power, how much power is consumed by your chip. There's Synopsys PrimeTime, I think power, Cadence Joules. Power information is used by multiple tools in your flow. The synthesis tool also uses power information to synthesize properly. Your place and route tools, of course, as let's say if you're using Multi-VDD, it has to know that information, connect multiple, create a physical layer for each of the voltages. So power tools, even during simulation, so each of the tool is now power aware, can use power information to generate it. In addition to that, there are low power static information and power estimation tools. So once you're done with synthesis, okay, let me see if there are questions before I go to the next topic. Is the scan chain testing is same as fault modeling? So fault modeling is something slightly different. Fault modeling is saying, okay, let's say your pin is always connected to VDD. Okay, so that is a fault. How do you model this fault? The modeling means the model for that would be that the pin is always stuck at one. So modeling is an abstraction of your chip defect. We do cover this in more detail in our DFT course, plus as in I can go over more detail in our Telegram group, but in the interest of time, I will continue. DFT is supposed to check physical defects. Okay, so this is an interesting question. So it's saying basically DFT is supposed to check physical defects, but physical defect will only happen at silicon, not at RTL level. So what is the importance of DFT? So here what you are doing is not checking that defect right now. Defect will be checked in real silicon. But so that in order to check it, you have to do DFT. In order to check it, you have to do DFT. Why do you have to do DFT is what I covered earlier, right? For example, let's come here to the scan chain, okay? So unless you have created the scan chain, you cannot check that. So you are designing in DFT, you're designing in your circuit in such a way so that it can be checked now after fabrication. For example, let's say you want to check this particular flop. Is it always stuck at 0 or always stuck at 1? Unless you have connected it to a scan chain and try to force a value 0 or 1, you will not be able to detect that and ensure that your chip is not faulty. So in order that your chip can be checked in after fabrication, you have to do DFT right at RTL level so that later on when it's fabricated you can test it. So the importance of DFT is that you're not testing now, you're modifying your design so that once it goes in fabrication you can test it. Okay, let me see. So yeah, recordings will be available later on. Which company requires from us as a design what company requires from us as a design verification depends on what level of experience you have. Let's discuss this more in our Telegram. Okay, let me see. Okay, I didn't see. Okay, let me continue. There are some more questions which I can cover in Telegram, but I do have this session to complete also. Okay, so let's come back to our post-synthesis STA. Okay, so now you had done some STA. Basically, now what we will do is you have designed your circuit, you have mapped it to the gate level. You want to make sure it is meeting my frequency goals. And how that is done is by doing static timing analysis. So static timing analysis is a method of verifying timing performance of a design. What is the timing performance? Like whether let's say I designed my processor to run at 1 gigahertz. Is it able to run at 1 gigahertz? Yes or no? I can check by using static timing analysis. Can I do this timing analysis using by other methods? Let's say, can I run simulation? Can I run spice simulation? Of course, you can do using that, but statics. There are some advantages of doing static verification, which simulation will be dependent upon test match. Static will be complete, so you prefer to do it using static verification. Okay, so static verification is static, is fast. It can launch a large design. It's exhaustive. It will cover all the scenarios. You will not have to write any test bench. It will cover all the scenarios, and that's why it's very important because you want to make sure your chip works for all the scenarios and not just for the test benches you have written. So static methods, that's why are very useful. It's conservative, that whatever there is some guard band, when once you verify it, it will work on your netlist. Static verification, static timing analysis does not verify the functionality. For example, let's say you wanted to implement an AND gate, and rather than that you implemented OR gate, it cannot verify that. It can only verify that whatever you have implemented will meet setup and hold time, will meet timing, will work for the frequency you are asking for, but it cannot verify the functionality. So that's why equivalence checking tool compare the functionality, you run simulation, other kind of verification to verify functionality. But static verification you use to verify the timing of your design. Static verification, static timing analysis works for only synchronous designs. For synchronous designs, it can verify the timing of your design. Does not verify for asynchronous clock domains and asynchronous portion of the design. For asynchronous clock domain, you need a CDC tool, which we talked about earlier, which you run at RTL level. But static timing analysis, you run at gate level to verify synchronous portion of paths between synchronous clock domains of the design. So what are the type of checks? So type of timing paths it checks. It checks for setup and hold timing. It checks for clock timing on the clock gates. It checks for async pins, reset can clear, your meeting timing and frequency goal, or maybe you can define particular checks from one data to another data, that also it checks. But the primary majority of the check which it checks is setup and hold time. That is the main goal of running static timing analysis. Okay, so setup check, as you know, is when you have a clock and a flock, your data on the flock should be available sometime before the clock edge. This is known as T setup, that is dependent upon technology and the flock. So sometime before it should be stable. After that, it cannot change. If you change, you will not meet setup time, or you will your design will not function properly. So this check is done by your STA tool, ensure that your data becomes stable at a certain time, which is known as setup time before that. And that is what STA tool will check during its run. So data becomes stable sometime before that. If that happens, it will say, okay, this check passed. But if it does not, it will say, okay, your check fails. Similarly, it will check hold check, that after the clock edge, for a certain time, data should still stay stable. This is known as hold check. The value of what this sometime is dependent upon library or technology you are working on, and that also is checked by your static timing analysis tool. It checks that you are meeting setup and hold time in it, and verifies that. If you're meeting setup and hold timing, your clocks can work on the frequency you intended to. Let's say you intended for 1 gigahertz processor, clocks can run on 1 gigahertz processor. If you cannot meet timing, then you have have to modify the design, you have to change your clock frequency to make it work for your design. So what are the inputs to the STA tool? It will check your gate level netlist, which is created after synthesis, which is libraries. So when you're doing at this level, you will have gate level netlist and library and design constraints, which are timing. What is the frequency of the clock? Well, like it needs to run at 1 gigahertz. This is what you will give as an input for a post-synthesis STA. STA, static timing analysis, also is run later after place and route. So there you will have more information. You will have what is the parasitics in the design, basically what are the inductance and resistance of various wires in the design, what are the delays in the design. So you will have much more information which comes from layout after place and route. So when you run STA after place and route, you will give additional these two information as well to run the STA analysis. It will also generate SDF file, which is standard delay format, delay of each of the logic nets in the design, which can be used in simulation. It will generate a timing report telling you, okay, whether you are meeting timing or not for setup and hold. I'm not going into detail of that. We have an STA course which goes into details of that. So not going in this overall flow webinar. Tools which are used are commercial tools are the Synopsys PrimeTime. There is Tempus from Cadence. In terms of open source tool, there is Open Timer. And I think there is something called Open STA as well, or something like that, which is open source tools. So commercial tools, of course, are better work for all kind of design, but open tools can also be used for small examples design and for learning. We do have a 5-day STA workshop which is coming up. Do check out our website for that, which uses open timer tools to explain the concept. Then once that is done, synthesis, and you have done post-synthesis STA, you will go into place and route. Let me check if there are any questions which have come up. Just take a and then continue. What are positive and negative slack? This is when positive slack is when you're meeting timing. Negative slack is when you're not meeting timing. We go as in you can ask this question again on Telegram group, and which I copied. There is, but in the interest of time, I'm not going into details of that. We also have STA course, as I mentioned, where you can go into details, or you can ask specific question in the Telegram group. DFT will come before fabrication or after fabrication. DFT means design for test. You will do it right at RTL, after RTL stage itself. But actual testing will come after fabrication. There is some testing done before fabrication as well. Okay, so let's come to place and route. So this is now purely in the backend domain. You are basically started from here. You have reached here. You are now going to map your gate into physical connections, physical wires, those things which will happen in physical design. So what are various steps in physical design? At a high level, these are the steps. You will do partitioning of your design. Then you will do floor planning, placement, clock tree synthesis, and all these steps. And then you will do physical verification. Let's go into little bit more detail of each of these steps. Partitioning is you break up the circuit into smaller subcircuits or modules, for which then you do physical design individually. So let's say you have this full design, you will break it into smaller portions. And each of these partitions then will be done physical design individually. Why do you break it? Just to make it easier, divide and rule. Sometimes the design is too big. It's not able to do, tools are not able to do physical design together. That's another reason to partition it. But it can be managed better, faster by doing partitioning. Then once partitioning is done for each of those partitions, you will decide where I will put each of those blocks. That is known as floor planning. You're planning where I will put each of the block. This block I will put here. This block I will put here. So you will determine the shapes. One is not everything needs to be rectangle. This can be irregular shapes, which you can physically define. You will put each of these, define the shapes and arrangement as well as location of these blocks, plus what will be my location of input pin will come here or here or here. All those things is then decided in the floor planning stage. And after floor planning, you will put exact placement of these cells. This cell I will place here, this cell I will place here. So you will assign the spatial location in your chip for each of these blocks. Once you assign spatial location, then you will start designing your clock tree, because clocks need to go to all of these blocks. You will design what is the path clock will take, how will you hook up the clock, whether it goes here, what is the actual connections, how clocks will reach to each of these blocks. Since clock goes to everywhere, it's a complex logic, so there are specific care you have to take care while designing the clock tree path. So it is done earlier. Then other than clock, you will do special connections. Let's say this block output port is connected to this block input port. You will connect those in the physical design using your rails or connection wires, which will go through in the design. So you'll connect those. That is known as routing, which is for design connection. You do clock tree earlier because clock is much more, goes everywhere in the design. So that has special take care. Has to be done. Design connections are not as much as clock, that comes later as and known as routing. Then you will, your place and route tool will do some types of timing analysis to make sure timing is being met, whether additional buffers are needed, high driving cells are needed, all those things. So basically, it will optimize the timing. That is known as timing analysis and closure. And then you will do physical verification. You will physically verify, now I have designed everything, whether as in your library will say, okay, this has to be the minimum width, this has to be minimum distance. Some things have to be so much away from each other. All these rules you will check in design rule checking. You will make sure, similar to equivalence checking of RTL versus netlist, you will do equivalence checking of layout versus schematic, whatever you've laid out and schematic, all these things you will do and make sure your design is correct. That is known as physical verification, and then you will take out the chip. So for physical design, typically tools which are used are IC Compiler, which is from Synopsys. There is Encounter, there is Mentera Prisa, and as in there are some open source tools available as well. So these are the tools which are used for physical design. Again, for physical design, we have a specific course. If you are interested in more detail, you can go into that course as well. Then you will do final sign off. You will previously STA sign off you will do previously when you had done certain information was not available, clock was not properly hooked up. Now you have actually created path for the clock, so you will have delays of that. You will have parasitic information now, so you will do sign off STA with all the information now to make sure your chip is still working correctly, and then say, okay, meet setup and hold timing, make sure everything is working correctly. So you will do STA again, which is called a sign off STA. Then, as I said, you will do other sign off checks. You will make sure design rule check is working correctly, whatever the spacing is needed. You will do equivalence checking, making sure whatever gate you have generated, whatever schematic which has been generated, they are matching. There is equivalence checking between that. You will check IR drop when voltage connects to metal wire. Before it reaches VDD, because of the resistance in the wires, there is some drop. And based upon, is the design going to work correctly even with that drop? If there are unwanted EM checks also you will do. Can it cause partial open and closed circuit? You will make sure your scan connections are correct. Any extra rules which is provided by your foundry, DFM, design for manufacturing, those also you will check. You will do power analysis to make sure your power is within what you are planning it to be. Since you have a lot more information, physical connectivity of the design, you can do all these checks before you tape out and say, okay, I'm done now. Okay, so you will do all these sign-off checks. But once that is done, you now will have a gate level netlist. You will do again verification. You will run your STA flow or your PNR tool will have generated something known as SDF, which will have standard delay information. Previously, when you had done simulation at RTL level, there were no delay information because actual design implementation and what is the length of each of these nets and wires were not known. Now all those are known, so now you still want to make sure that my design is still working correctly even in the presence of this delays. So you will run simulation with this, that even in the presence of these delays, my tests are working correctly. And then once the verification is done, you will tape out your chip. Now, sometimes, as you know, right, as in we have been doing a lot of verification after place and route, during synthesis. What if you found a bug? What if something needs to be fixed? So you don't need to redo all the flows. Tools allow you to do something called engineering change order or ECO flow. During ECO flow, you will close all the sign-off checks, or basically make sure everything is working correctly, and also fix issues. So when you fix issues, tools allow you to make small changes. Let's say you found a timing issue. STA tools allow you to do ECO changes, where basically small change will be done to meet timing. But then if you make any change, you have to do all the verification again. You will have to maybe run gate level netlist again, verification again, maybe run timing analysis again. All those things are need to be done again. Always make sure chip needs to be worked correctly. Okay. Once that is done, you will go into fabrication. Okay. So fabrication is when you have given your layout information to the foundry, and foundry will now, based upon this layout information, start making your chips. So there are multiple steps. Of course, we're not going into details of each of those steps. First will be lithography, basically where you will get a foundry will have a silicon crystal or ingot. They'll get a polished wafer, and they will basically put light on it to create your specific chips based upon the layout information you have provided. You will remove undesirable material from the wafer selectively during etching. Then basically you will create a chip, and that will be shipped out before, as in that after that the packaging will be done, and then that will be shipped out. So there are multiple steps involved in fabrication. We're not going into details of each of those steps in this particular webinar, but these are the steps which are involved. Then you will do packaging. Whatever chip you have created, you will put a casing around that chip to make sure, and proper pins will be placed, so as to make sure it can be used. And secondly, the outside environment does not make the chip, does not impact the chip. So basically, it's essentially an encasing of your chip to protect it, and that is known as packaging. Once you package it, you will then test it. Your chip will put it in the tester, or wafer will put it in the tester. The tester will check. You will check here. It's meeting the performance goal. It's meeting the frequency goal. This can also be done. This typically actually can be done before packaging, so that you can test wafer by wafer. That is how it is done. And then after that, whatever chips passed, you will do packaging for only those chips, because those are the chips you need to ship it to your customer. So this covers all the VLSI flow. I will talk about some of what are the various profiles in VLSI, and then before that, I will check if there are more questions. Okay, so please explain sign-off check. I would suggest to join Telegram group. You can answer everyone, and I can also help out. The link to the Telegram group is slightly above this, and then it's also available on our website. There is a question: what are DFM checks? These are designed for manufacturing checks. These are the checks given by your foundry. Okay, you should run these checks before you can fabricate your chip. So let's talk about what the career roles in VLSI said. This is based upon one of the book, which is available on Amazon, the VLSI handbook. So at architectural levels, there are architectural exploration, which is done, hardware, software, what should be put in hardware and software, how do you model SOC, performance analysis. These are typically roles for more experienced people, which basically have worked in the industry earlier, either in front end, back end, so that you can start thinking from the architecture point of view. Then in front end, what are the roles which are the jobs which are done, and based upon that roles are available. So typically RTL design related, there is people who are developing HDL, RTL, either it can be IP or maybe doing SOC integration. There are people who run static checks, which we talked about, lint checks, CDC, low power. So there are jobs and profiles and roles in that. Then there are jobs and profiles for doing handling synthesis, like defining timing constraints, optimizing timing the synthesis. Then DFT related, how to design DFT, how to run DFT tools, how to design BIST, memory based or logic based. Then one kind of job is to run actually equivalence checking tool or do equivalence. Typically, this is done by the same person, but it can be different also depending upon what those are. Then there are sign-off checks, physical verification, static timing analysis, which are done. So these are the typical kind of roles in front end. Then roles in back end is typically you will run PNR flow. If the design is really complex, different people may be working on these steps in the PNR flow, or same people may be working. Or depending upon the chip size, sign-off checks sometimes are done by a separate set of people to ensure correct verification different from design. The roles in EDA companies, as in EDA companies have R&D engineers. These are tool companies, like people who are writing C++ code to design these tools. Then there is product engineer who are defining what features should be there in the tool. Then there are application engineers who are helping to run the tool at the customer end. Then people basically marketing about those tools and doing sales of those tools. So these are typical roles in EDA companies. So this covers today's webinar. As I mentioned, there we have a free community Telegram group. The link was shared in the chat window. You can also join. You go into our website. You can follow our LinkedIn page. For any other questions or support, you can mail us to support@vlsideepdive.com.